The smart grid currently works with a centralized platform or intermediaries to provide services such as billing, monitoring, bidding, and energy transmission. The introduction of new technologies along with the diversity and expansion of energy sources complicates the management, control, and operation of the energy sector. There are 5 main challenges in the smart grid, and we will discuss how to face them with blockchain technology later. To make it clear about the blockchain and the smart grid, we can see the framework of this video at first. New technologies, high investments, lack of accurate information, etc. complicate the coordination between actors in the energy sector. The current smart grid system faces the problem of energy balancing. Energy suppliers and traders typically request an estimated amount of energy from generators based on their demand analysis. Such an estimate can be inaccurate due to a lot of factors. Therefore, it is important to establish close cooperation between relevant players such as generators, distributors, retailers, consumers, and regulators to facilitate grid management. Both physical and technical problems can contribute to imbalances in power generation and consumption. The failure of some network components, interference from third parties, vandalism, and natural causes can contribute to imbalances in power supply. Technical problems such as malicious attacks, frequency deviations, overloads, synchronization losses, and voltage dips can also contribute to power imbalances. Therefore, it is essential to control and monitor the power supply in each period. However, this becomes a challenge due to the number and diversity of power generation methods and regulatory requirements. Current smart grid data management faces the problem of data aggregation quality, security, compliance control, common scope, and efficiency of the management mechanism. A large amount of data is generated and transferred between different entities. Accurate and consistent incoming data streams are important to avoid sudden and unexpected power supply disruptions. But the data collected tend to be quite large, as multiple smart grid domains are involved in the process. So there is also a regulatory requirement to provide accurate data as frequently as possible. Distributed automation devices are used to decentralize the operation of the grid. Decentralizing grid operations allows stakeholders to control and manage their data locally. These are devices such as phaser management units, remote terminal units, supervisory control and data acquisition, and smart meters that are used to collect and monitor data. This management and operation of distributed energy resources is complicated. Further work is needed to facilitate coordination between decentralized and centralized stakeholders. The operation and management of the smart grid brings security and privacy challenges. The supervisory control and data acquisition module in modern power systems collects data at remote terminals, transmits, and stores it in plain text to the main control center. This centralized data collection and storage is highly vulnerable to cyber attacks. Over the years, several cyber attacks have taken place on the smart grid. Therefore, security is one of the biggest and most difficult challenges facing the current smart grid. The exact definition of blockchain technology differs depending on the desired function and specific implementation. Blockchain is a collection of technologies including peer-to-peer networks, public key cryptography, fault-tolerant consensus algorithms, smart contracts, and database management technologies. And they together form a low-cost, secure, and efficient operational management system. Each block is encrypted and linked to the previous one by hash technology, which makes it more difficult to invalidate older blocks. Each new block is accepted after a validation and consensus decision process. The number of blocks in the chain is unlimited. The more blocks, the more secure the system is. Participants in the blockchain network can view or add data without central coordination controlling the process. This makes the blockchain system autonomous. A typical blockchain transaction can be divided into 3 phases. First, there is the transaction request, where a node requests the creation of a block by sending data with a specific value to another node within the network. In this phase, a hash code is generated and distributed to all network nodes. Second, all nodes within the network verify the validity of this block based on a previously established consensus mechanism. The feed, a node that makes a real effort and finds the correct hash value, is awarded as the winner and thus is entitled to add the latest block to the chain. Blockchain offers a new solution to the challenges mentioned before. It minimizes data management, fair incentive mechanisms, regulatory costs and technical issues, transaction fees between distributed nodes, speed of resources, and price adjustment issues. It can also increase transparency among stakeholders, ensure data security and privacy, simplify the energy demand and supply chain, and minimize distribution losses. Therefore, countries around the world are recognizing the potential applications of blockchain in the energy sector. The consortium blockchain is used to support the virtual power plant control system, improve operational activities, optimal scheduling, efficient trading, real-time performance, low transaction costs, information security. Lian developed a virtual power plant control system model based on blockchain. The model integrates discrete power supply, load, and other smart devices to share data with two blockchain systems, one technical and one commercial. The technical blockchain controls the process by connecting to the supervisory control and data acquisition system via Ethernet to support power transmission, balancing, voltage, and frequency control, and to provide stable transmission and scheduling for the virtual power plant. The commercial blockchain supports the process of energy quantity, price, transaction contracts, etc. Blockchain provides a mechanism to synchronize data from a variety of sources. These can help grid operators monitor different energy resources simultaneously, control voltage and frequency, and coordinate communication between different energy stakeholders. Blockchain can also help regulate voltage and frequency on the smart grid. With blockchain technology, we can accurately and continuously determine the amount of energy produced and consumed, so that the grid is resilient to unexpected frequency or voltage overloads. In addition, Madhu GM has proposed a framework for using blockchain to monitor photovoltaic-based electric vehicle charging stations to regulate load frequency. The proposal integrates blockchain with a smart energy controller to optimally manage grid capacity considering load frequency and photovoltaic availability. The proposed framework improves user privacy, the immutability and transparency of energy data, energy tracking and availability, and sharing among users. Blockchain can support the smart grid data analysis and management, data protection, and aggregation. Along with the diversity of distributed generation, the smart grid is also changing its data aggregation and analysis mechanisms. Aggregators such as demand response and virtual power plant provide grid services to a wide range of energy resources. However, these aggregation mechanisms pose challenges to operators due to their large scale and complex deployment and therefore require management and control. Liangshan proposed a blockchain-based power grid data management architecture to realize binding data recording and business collaboration among multiple nodes. The framework promotes collaboration among data aggregation and analysis processes, provides real-time awareness of data sharing to various stakeholders. It can simplify the process of data access, coordinates data application, and facilitates technical support for smart grid data management and operation. Blockchain can also be used for decentralized data collection, analysis, and management to minimize data communication and storage costs. Integrating blockchain with advanced metering systems could help utility operators predict future consumption needs by monitoring the data provided by blockchain technology. Adedeo Adarabol identified 3 blockchain-related characteristics to analyze the smart grid-related literature and identify requirements for National Institute of Standards and Technology conceptual models. They think blockchain enables the decentralized collection and verification of metering applications at multiple levels and solves the problem of centralized data collection that could potentially affect smart grid performance. Luosini's group decentralized data aggregation for microgrids using Pallier and practical Byzantine fault-tolerance homomorphic encryption is proposed to protect user privacy and data integrity in public storage and sharing. They have also proposed an automatic and distributed solution for energy distribution in a microgrid using Ethereum smart contract. Their framework minimizes reliance on a central authority, improves the efficiency of renewable energy resources, and addresses privacy and security issues. It has been shown that these blockchain-based systems can support the physical layer of the smart grid. Aggregation, analysis, and management of grid data can improve the missions of transmission system operators by providing accurate data on electricity generation, distribution, and consumption. Blockchain, along with various underlying technologies, can facilitate decision-making at different levels of grid operations. Traditional smart grids have been subjected to a number of malicious cyberattacks over the years, resulting in partial or complete power outages. Blockchain, whose main characteristic is the immutability of data, can provide a solution to this problem. Several promising blockchain-based techniques have been proposed to address privacy and user security challenges in the smart grid. Privacy-preserving energy transactions is described as a secure distributed ledger-based energy trading solution that provides anonymity for communication, bidding, and trading. The framework enables secure and verifiable trading of energy futures, preserves prosumers' privacy, and allows distribution system operators to regulate trading and enforce security rules. A permission-based blockchain edge model for smart grid networks to ensure data privacy and energy security is proposed by Kiki Gai. The proposed model aims to ensure the traceability of energy consumption while protecting end-user privacy, enable optimal energy management, and enable controllers to assess the identity of the edge device in smart grid networks. Roberto Casadovara showed how the immutability of the blockchain can be used to detect non-technical frauds such as energy theft, metering errors, billing process errors, etc. This helps utilities control and monitor the power distribution network. We have systematically explored blockchain-based applications for the management, control, and operation of smart grid systems. We focused on the 5 main challenges: stakeholder collaboration, grid imbalance, data management and operations, decentralization of grid operations, and security and privacy. It has been demonstrated that blockchain technology can be used to support smart grid infrastructure management and operations. Existing technologies leverage different blockchain architectures for different application scenarios. However, actual implementations of the technology for grid management, control, and operations mentioned before are still sporadic and localized. Therefore, there is still a long way to go for us to explore the blockchain technology.